Hi, everyone. It is my absolute pleasure today to introduce Victoria Krakovna. Victoria is a research scientist at DeepMind working on AGI, that's Artificial General Intelligence Alignment. And before that, she worked also on interpretability. And she is also the founder of the Future of Life, a co-founder of the Future of Life Institute, which in my layman's understanding is trying to prevent the bad version of the singularity and hope more for the good version, amongst other technological restraint goals. So I'm very, very excited to hear what she has to say. As we go, I guess, Madeline, please correct me if I'm wrong, questions should be entered into the chat and at any point during Victoria's talk, and I will find the time to pass them on to Victoria.
Great. Thank you so much, Jen. So yeah, I'll get started. Hi, everyone. I'm Victoria. I'm a research scientist in AI safety at DeepMind, and I'm going to give you my overview of AI alignment. And please note that this presentation reflects my personal views and not those of DeepMind. So the goal of AI alignment is to figure out how we can build advanced AI systems that do what we want them to do and don't knowingly act against our interests. We find that this is quite a hard problem because, first of all, it's hard to specify what we want, and we often run into Goodhart's law, where a metric becomes a target, then it ceases to be a good metric. And one example of this is like the tale of King Midas, who asked everything he touched to turn to gold, but the way that he specified his desire for gold had some very bad outcomes for his other preferences, like being able to eat food. And when we specify the objectives of AI systems, then we can often unwittingly end up in the shoes of King Midas. We have lots of examples of Goodhart's law with AI systems today. And I expect it's only going to get worse as our systems get smarter and better at optimizing the wrong objective. And even if we do manage to specify what we want correctly, we're still not done because the AI system can still learn unintended goals. For example, there are some instrumental sub-goals that are useful for any objective, for example, avoiding shutdown and having more resources and so on. So overall, alignment is a pretty hard problem. And we expect that at some point, humanity might build artificial general intelligence, which we can define as an AI system that can essentially automate all of the human activities that are needed to speed up scientific and technological advancement. And if we don't succeed at aligning these AGI systems and getting them to do what we want them to do, that can be pretty bad news for us, because a powerful AGI system that pursues the wrong goal could potentially be catastrophic for humanity. This kind of AI system could sacrifice things that we actually care about in service of this undesired goal, and would also have an incentive to stop us from interfering, which is one of those convergent instrumental sub-goals. So the focus of this talk is how can we avoid this and build an aligned AGI system instead. So let's take a high-level view of the AI alignment field. I would divide this work into alignment components, which focus on different elements of an aligned system, and alignment enablers, which are research directions that make it easier to get the alignment components right. And of course, this doesn't include everything going on in the field, since there are a lot of topics that don't fit into this kind of neat and simple taxonomy, but I still find it useful to think about the field in this way. And now we can take a look at these different research areas in more detail. But to identify the components of an aligned system, it can be useful to consider different levels of specification of the AI system's objective. We start with the ideal specification, which represents the wishes of the designer, what they have in mind when they build the AI system. And then we have the design specification, which is the objective that we actually implement for the AI system. For example, this could be a reward function. And finally, you have a revealed specification, which is the objective that you can infer from behavior. For example, the goal that the system actually seems to be pursuing. And then if your revealed specification matches the ideal specification, then you actually have an AI system that is behaving in accordance with your wishes. And the gaps between these specification levels correspond to different alignment components. So we have outer alignment when the design specification matches the ideal specification, For example, when you manage to design a reward function that perfectly represents your wishes. We have inner alignment when the revealed specification matches the design specification. For example, when your system is actually optimizing the reward that you specified. And of course, there are also some very important questions about what should go into the ideal specification and how to make it representative and fair and so on. And AI alignment is trying to solve a complementary problem. How can we reliably set the goal of an AGI system at all? So we could say that AI ethics focuses on the what question, what the goals of the system should be, while alignment focuses on the how question. How do we align the system with any given goals that we choose? So yeah, these are, you could view these as two complementary problems. And now we can take a look at how we can make each of those alignment components happen. So one significant challenge to achieving outer alignment is scalable oversight. How do we give good feedback to the system in domains that are hard for humans to evaluate? For example, if the system comes up with a complex plan or a scientific breakthrough or something like that, whose consequences we don't understand. There are some promising proposals in this area that use AI to assist the human evaluator. One such approach is iterated distillation and amplification, IDA, which recursively amplifies human judgment with the assistance of AI. So here you start with an agent A that's imitating the judgment of a human H, which is the distillation step shown in purple. And then you use this agent to assist human judgment at the next level, which is the amplification step in orange. And this gives you an amplified human HA. And then you can repeat the distillation step by training an agent A+ to imitate this amplified human and so on. And a related proposal for scalable oversight is safety via debate, which can be viewed as a way to implement amplification for language models. Here you have two AIs, Alice and Bob, that are debating each other to help a human judge decide on some question. And these AIs have an incentive to point out flaws in each other's arguments and make complex arguments understandable to the judge. And one key assumption in debate is that it's easier to argue for truth than for falsehood. And so a truth-telling debater would generally have an advantage. So debate is using this kind of self-play setup to enable the human judge to evaluate complex questions that they otherwise would not be able to evaluate. Now we can have a look at inner alignment, which usually happens through goal misgeneralization. This is when an AI system learns an unintended goal and then competently pursues that goal under distributional shift. And this happens because the agent's capability is generalized, but its goal does not, which means that your system ends up competently doing the wrong thing. So it could actually perform worse than, for example, a random policy on the intended goal. And this is an underspecification problem, where the system only observes the design specification on the training data. And so a number of different goals might actually be consistent with the information that the system receives. And so it could learn an incorrect goal from the set of goals that are compatible with the training data. And so this problem can arise even if we get outer alignment right, even if the design specification of the system's objective is correct. And yeah, I've been collecting examples of goal misgeneralization, so you can find some in this spreadsheet. We have some empirical demonstration of goal misgeneralization with current systems. For example, here you have a reinforcement learning agent that's playing the coin run game, where the agent is trained to reach the coin at the end of the level. And then if in the test setting you place the coin somewhere else, it turns out that the agent ignores the coin and still goes to the end of the level. So it seems that the agent has learned the goal of reaching the end rather than the goal of getting the coin. And here we can see that the agent's capability is generalized because it can still avoid obstacles and enemies and traverse the level. And generally it's acting competently, but its goal does not generalize because it ignores the coin. So it's competently pursuing the wrong objective. And this problem is not just limited to reinforcement learning. So here's an example for a language model where the model is prompted to evaluate linear expressions involving unknown variables and constants. And to solve these expressions, the model has to first ask about the values of the unknown variables. And so it's given some training examples. In each example, you have two unknown variables. And then at test time, if it's given a question with a different number of unknown variables, it still does fine if there's one unknown variable or three. But then if you don't have any unknown variables, we find that it's still asking redundant questions. Like if you say, please evaluate 6 plus 2, it will ask, what is 6? Even though it could give an answer right away. So it seems like the model learned to always query the user at least once before giving an answer. So it has not learned the right goal of like giving an answer as soon as it is known.
Can I ask a question?
Yes.
Or rather, from
sure.
the audience, from Ahmed Mustafa Anis, who's asking, can an unintended goal be considered, like when a system interprets a goal in an unintended way, be considered a form of multitasking?
Sorry, can you repeat the question again?
If a system at test time interprets the goal in an unintended way, or misgeneralizes the goal, could that be considered sort of a form of multitasking?
Maybe. I think it depends. It depends what you mean by multitasking. But yeah, I think that I guess the issue is that during the training process, those two goals kind of were not distinguishable. For example, in the coin one example, if the coin was always at the end, then when the agent was doing well, then it was always like achieving both of these goals. So it could say in that way it was, multitasking between those goals. But yeah, I'm not sure whether it's kind of what you get out of like thinking about it in that way. But then when it's if it's generalizing the goal incorrectly, then kind of it's no longer achieving the intended objective in the new setting. And this can happen. Like we have some other examples where like even if the system has enough information to distinguish those two goals, it might still like generalize incorrectly.
And then maybe I can also ask a question that I have, which is that if you go back to this human amplification, is there also a role in that for like somehow crowdsourcing or also collecting feedback from multiple humans? Because there's not, or is alignment really meant to align with just like one human's perspective?
I mean, you can apply these methods to multiple humans as well. So if you are using human feedback to align the system, then you can I think you can have like a variant of debate with multiple judges who maybe all have to agree, or like some way of aggregating their feedback or their judgment in some way. So I think these are kind of composable techniques. So like so techniques like IDA and debate are meant to ensure like informed oversight, where, for example, the two AI opponents might point out when one of the AIs is lying or being deceptive, or when there are some considerations that the human judge has missed. And that can also apply to multiple judges. So yeah, so I think this is a complementary problem to which human values you're trying to align to, or like how to get feedback from multiple humans. So like if you have a solution to that and a solution to debate, then I think you could just put them together.
Great, thank you.
Yeah. So just when you were presenting these methods, then for simplicity, we're talking about a single human judge or a single human designer. But yeah, you can do the same thing with multiple judges.
One more question, actually. So for the Gopher example, is it Ergun wants to know if this is because the types of questions the model sees are mostly with unknowns in them?
Yeah. So yeah, basically, like when the model was kind of prompted to do this task, then the prompt included like basically a few short examples of doing the task, and then those questions had unknowns in them. So I think if there was a more diverse set of questions and some of them didn't have unknowns, then probably it would have generalized better. But this is, yeah, this is also like an example of how it's an underspecification problem where you like it was not given examples with like all the different numbers of unknowns. So yeah, actually this brings us to mitigations, where one possible mitigation for Kgomo generalization is to have more diverse training data. So for example, if you put the coin in different places, or if you have different numbers of unknowns, then some of these Kgomo generalization problems go away. But yeah, we expect this mitigation alone will not be sufficient because it's hard to get diversity in all of the relevant variables that you might care about. Maybe you can think of the position of the coin or the number of unknowns, but you might not think in advance about some other variables that turn out to be important. So yeah, so we want to do this in addition with other mitigations. And then the possible approach is to try to maintain uncertainty over the goal, for example, by trying to represent all the possible goals that are consistent with the training data, though generally we expect this to be difficult to characterize this set of possible goals. And then I think it runs into some of the same problems as like maintaining diversity over all the relevant variables. And another aspect of mitigating goal misgeneralization is that we can focus on the most concerning case of goal misgeneralization, which is if the training process produces a deceptively aligned model that is not only pursuing an undesired goal, but also is aware of this goal not being what we want. And so like the deceptively aligned model would actually try to hide this fact from its designers. So this is the case where the model would actually know that its actions are not in line with the designer's intentions. And we can develop mitigations for goal misgeneralization that's specifically targeted at deceptive models, because this is like a particularly concerning case, especially for AGI. So one thing we could do would be to use interpretability techniques to provide feedback on the model's reasoning, or to detect deceptive reasoning. We could use scalable oversight methods like debate, where the opponent AI might be able to point out deception. So yeah, so this is the deceptive model case is in some ways a more difficult case, but in some ways we can also develop specific mitigations because we can make more assumptions about the model, in particular that like it's kind of knowingly doing the wrong thing. So yeah, so this was an overview of the components. Any more questions before we go into the enablers? The enablers, we can start with mechanistic interpretability, which aims to build a complete understanding of the systems we built, and could help us understand the reasons behind systems' behaviors and potentially detect undesired goals of the system. So the work on reverse engineering vision models, for example, studies individual neurons and connections between the neurons to discover meaningful features in circuits, where circuits are subgraphs of the network, which consist of a set of linked features and their weights. For example, here's a circuit that shows how a car detector neuron relies on lower level features like wheel and window detectors, because it's looking for wheels at the bottom and windows at the top of the image, as you can see from the colors. And some more recent work which is focused on reverse engineering language models, and they've actually found similarly meaningful components in circuits and transformers. For example, they found a special type of attention heads called induction heads that explains how these transformer models adapt to a new context. And even though transformers are quite different from vision models and they have a different architecture, it seems like this work has found some similar principles, like looking for circuits that help understand these different types of models. And this makes me a little bit more optimistic about being able to understand more advanced AI systems in the future, even if they have a somewhat different structure from today's systems. There's some generalizable principles here. One thing that mechanistic interpretability can be useful for is understanding and predicting phase transitions in AI systems capabilities. And rapid phase transitions is a central worry in alignment, because if the system's capabilities suddenly become better, but they suddenly generalize, but the alignment of the system doesn't generalize as well, then it would make the system difficult to control. So predicting phase transitions and capabilities can be quite important. And one interesting phenomenon here is grokking, which is when there is a sudden improvement in the test accuracy of the model long after it achieves perfect accuracy in the training data. And there's some interesting recent work that defines some progress measures that vary smoothly, even as the model's performance is discontinuous. And this can be used to understand the mechanics of grokking. And they actually identified 3 different phases of the training process, where first the model memorizes the training data, and then it forms some circuits when the network learns some kind of mechanism that actually generalizes. And then it will clean up these clean up the components that do memorization. So it starts just by memorizing the training data, but then it learns, it gains some more generalizable understanding of what's going on, and then it forms circuits that represent that. And yeah, this is an interesting paper that explores this. So we hope that work on understanding these kind of phase transitions will be helpful in predicting of how AI system capabilities will develop.
So Max Marion wants to know, is there any evidence of models with deceptive goals already existing, as in deliberately hiding its goals from the creators, and not like other players like the diplomacy model? And why would this happen?
Yeah, so far, the models we have now are, we expect they're not very goal directed yet. So we have general examples of goal misgeneralization, but yeah, I think we don't have concrete examples of kind of deceptive alignment, at least a strong version of deceptive alignment. So the deceptive alignment also requires the system to have an understanding that it's it's an AI system. It's being trained by human designers in a training process and so on. And that's something that we can expect AGI to have, but I think current systems don't have yet. So, current language models will often they'll be able to answer this kind of question. They will say well, I'm a language model being trained by OpenAI or whatever to do such and such, but they don't have this kind of strategic understanding of their place in the world, in a way that would produce deceptive alignment, which I think is also this is a good thing, because if we already had examples of deceptive alignment, then I think that would mean that we have more advanced systems that are kind of closer to AGI, and that would mean that we probably don't have that much time to solve these problems. We do generally see examples of deception for example, in language models. And we have some examples of what could be considered strategic behavior. I think, I have a later slide where I show an example of how language models learn what is called sycophantic behavior, where they learn to just agree with the stated views of the user. So whatever views the user is expressing, the model will agree with them. And that's yeah, that's not like deceptive alignment per se, but I think that's showing the kind of like influence-seeking behavior that I think can be concerning, especially if it's, if it goes further. So yeah, there's some theoretical arguments about why we might expect deceptively aligned models to arise, but I think thankfully, yeah, we don't have them yet.
Give it a couple more years.
Well, yeah, hopefully not that soon, but yeah, ideally we would want to detect early signs of deceptive reasoning and like situational awareness, where by situational awareness we basically mean like the model has an understanding of its place in the world, or how it's being trained, and like those are kind of prerequisites for the model to learn to like. This is also called like playing the training game, where the model would kind of like behave in an aligned way, but would be trying to pursue some other objective. So yeah, like ideally we would want to like be able to monitor the models we trained for those early signs of deceptive alignment, so we don't actually end up with a deceptively aligned model, because it would be kind of difficult to correct.
And one more question from Vladimir Hasia, who says, this is so interesting. He was just wondering, what are the worst scenario, like real life tasks that today's models can learn as sort of misgeneralizations? So for instance, like some type of robot figures out that they need a continuous energy source and, starts fighting for that plug or something like that.
So is this question about like what are some hypothetical scenarios for present day systems?
More like today.
Like, or real examples?
Like the worst thing that's happening today.
Yeah. So far, like, we don't have these. I think we don't have like really concerning examples of goal misgeneralization in deployed systems. So we also like we've just started collecting those examples. So I think we expect more examples to come up in the next few years. But I think you can observe the kind of examples with language models like the one I showed. So like I wouldn't worry about like goal misgeneralization of current systems necessarily, like causing a lot of harm today. This is it's more like these examples, even though like in themselves they're not particularly harmful, like the coin one example or the linear expressions example. It allows us to study this phenomenon and understand it better, which will be useful when we have more advanced systems that can actually do where goal misgeneralization behavior would be more harmful. So some alignment work focuses on understanding particular bad incentives that AI systems are likely to develop. And we can start with some incentive problems in outer alignment. So one very central incentive problem is specification gaming, where the system is exploiting some flaws in the design specification. So here, for example, you have a boat racing agent, the video on the left, which was rewarded for following the racetrack using those green blocks. And this worked okay until it figured out that it can actually get more reward by going in circles and hitting the same reward blocks over and over again. And then it was still getting more reward than the intended behavior, even though it was crashing into everything and catching on fire. And this is one of the best known examples of specification gaming. And here, like, this is a problem with a hand designed reward function. But there are also examples of specification gaming for learned reward functions and generally for reward learning settings. For example, on the right here, we have this robot hand, which was supposed to be grasping an object, but instead it learned to hover in front of the object, which was enough to fool the human evaluator into giving a positive reward. And there are lots and lots of examples of specification gaming. I have a list of about like 60 examples of this kind of behavior, which you can check out here. A lot of them are kind of funny. And so far, there has been some progress on understanding this phenomenon. For example, the paper that I linked here categorizes different types of misspecification. It also quantifies how the degree of specification gaming increases with agent capabilities. So the more capable the model is, the better it gets at specification gaming. And another common bad incentive is to cause side effects in the environment, because it's difficult to specify all of the things that the agent should not do while pursuing its goal. And this can be considered a type of specification gaming, because here the system is exploiting the fact that some considerations are omitted from the reward function. For example, here in this picture, if we don't specify that we want the vase to be intact, and this is equivalent to assuming indifference about the vase, and so the agent would be willing to collide with the vase to get to the goal faster. And so far, we've come up with some ways to measure the agent's side effects in the environment. For example, how much the agent's actions decrease the available options. So in this particular example, if the agent breaks the vase, then it's decreasing the available options that have to do with using the vase later, for example. And another line of work is trying to understand conversion instrumental subgoals. Some subgoals are useful for any objective. For example, avoiding shutdown, seeking power, influence, and resources. There are some theoretical results showing that most reward functions incentivize power-seeking actions. So it's hard to completely rule out power-seeking. And we expect that both outer and inner misalignment can result in power-seeking behavior. So for example, it can be unintentionally rewarded by human feedback, or it can also arise from goal misgeneralization. And we have some examples of power-seeking tendencies in present-day AI systems. For example, when fine-tuning language models with human feedback, they found that this can encourage influence-seeking behavior, like agreeing with the stated views of the user. So this is the example that I mentioned before. So non-fine-tuned model doesn't have this tendency, but fine-tuning with human feedback makes the model more sycophantic. So it seems like the human feedback is inadvertently rewarding that behavior. Now we can take a look at some of the foundational alignment work that helps us to do better alignment research. For example, since a lot of the concerns about AI alignment are about AI systems pursuing undesirable goals, there's some alignment work focusing on better understanding what do we mean by goals and agency and goal-directed behavior. The one research direction in the space investigates what it means to be an embedded agent that's not separate from its environment. And this is not so much the case for present-day AI systems that often have a clear Cartesian boundary. For example, reinforcement learning agent that specific action space. But this is more likely to be the case for AGI systems. And enforcing a Cartesian boundary for an AGI system might be more difficult because it has a very broad action space and a complex world model. And this embedded agent setup has posed some unique challenges, like dealing with self-reference and sub-agents and so on. So there's like a body of work trying to better understand that and develop some theory around that. And besides understanding how the goals of AI systems work, it's also helpful to understand how their world models work. And one research area in this space studies abstractions, in particular, whether there are some kind of natural abstractions or concepts about the world that would be learned by any agent or any system acting in that environment. And this is called the natural abstraction hypothesis. And if this turns out to be true, this would mean that AI systems are more likely to acquire human-like concepts as they build their models of the world, because any agent would acquire similar concepts. And this would make interpretability easier and also make it easier for us to communicate to our AI systems what we want them to do. So if this turns out to be true, that would be good news. So this is it for my whirlwind tour of the AI alignment landscape. We have any questions at this point?
There's just one question that just came up. Someone says that they've seen AI alignment referred to as a meme on Twitter, on ML Twitter, and they're asking what is the relationship to it?
A relationship between AI alignment and what?
I guess I really don't quite get the question.
I mean, if you can share the meme, I might be able to better answer the question.
Yeah, I guess one of the things that people are concerned about are on the scaling hypothesis. Could that be considered as under Goodhart's law?
The scaling hypothesis, meaning that, like, so are you talking about the inverse scaling hypothesis or the
classical scaling hypothesis? Could that?
Oh yeah. So you mean that, like, if we just scale up our models, then we could get to AGI without any, like, necessarily any further insights?
Yes, and could that be considered a case of Goodhart's law, whereby that measurement, the way we are approaching it, might affect how we get to that outcome?
Do you mean? I'm not sure I entirely understand the question. The measurement. Do you mean the measurement of scaling, or?
Measurement of scaling, could it somehow fall under Goodhart's law?
I guess, like, I mean, as far as I understand the scaling hypothesis, it just says that, like, as you scale up the model, if you, like, if you use more and more computer, the model has more parameters, more data, then eventually you can get to AGI with current architectures. So I don't think. I mean, of course, yeah. This might have, like, somewhat different outcomes depending on how you kind of how you model the relationship between, like, the kind of, how many parameters you need and how much data you need. But I think it's just saying that, like, in the limit, if you have enough parameters and enough data, then you might be able to get to AGI that way. So yeah, I wouldn't call this an example of Goodhart's law. I think when I was talking about Goodhart's law, I was like, I was talking about, like, specifying the goals, like the objectives of the AI system, and how to make that aligned with what we actually want the system to do, and that's how our Goodhart's law comes into play. And
right.
Yeah, and I think, like, I think the implication of the scaling hypothesis for alignment is that, like, it might not take that long necessarily to get to AGI if there are not a lot of fundamental insights left, then, like, we can extrapolate the amount of computed data that we're likely to have in 5 years or 10 years, and, like, see if that's enough to get to AGI. So this is the kind of forecasting angle on how much time do we have to solve alignment problems. And then it's also, this is also relevant for various questions of AI governance, like how to ensure kind of coordination on, like, best practices for developing advanced AI systems. If we find that it's that AGI might happen soon, that has different implications than, like, if AGI happens much later, because the set of relevant actors will be different, and there are different kind of strategic implications. So so I would say that's kind of, these are the kind of implications of the scaling hypothesis.
And Jan has a question about, for you, what are some interesting directions that and which ones do you think are dead ends?
So let's see. I think scalable oversight is a very important problem that I think has to be solved in order to solve alignment. And yeah, mechanistic interpretability is, I think, going to be like a key ingredient, because without being able to look inside the model and identify like what kind of beliefs does it have, what kind of goals does it have. If we only look at behavior, it will be hard to figure out that whether the model is aligned or whether it's just pretending to be aligned. So that's going to be a key element. Yeah. I guess I think also compared to my work maybe 5 years ago, I think like inner alignment is maybe like more of a bottleneck now than at least some of outer alignment. Like it seems like I think we are like closer to a solution on outer alignment than an inner alignment. So I think that's like reasonable to focus on. I actually have I do have one more slide about what people can do and how they can get involved. So maybe that might also answer some questions that are coming up right now. So yeah, we could just go through that and then get back to the questions.
That sounds great.
Yeah. So if this talk got some of you excited to learn more about AI alignment, you can check out my list of AI safety resources, where I keep a list of research agendas and selected work in those different areas that I went over in this talk, and also project ideas if you'd like to try working on AI alignment. You can also take the online AGI Safety Fundamentals course, which goes into more depth on all of these topics and comes with some fun exercises. And if you're thinking that you might be interested in working on AI alignment, you can check out the AI Safety Career Review by 80,000 Hours and see if it's a good fit for you to do alignment research. There are also various alignment fellowships and programs where people who are interested in alignment can work together on various projects and get some mentorship from my alignment researchers. So there are things like AI Safety Camp, the Alignment Theory Scholars Program, Machine Learning Summer School, and so on. And one thing I would encourage you to do is to think about the gaps in the alignment landscape. Like, what are some important components of building safe AI that we might be missing? Are there better ways to break out the problem space? And what is the next research agenda that maybe needs to be written in this space? The alignment is still quite a young field, so there are lots of open problems and a lot of framings of the problem that maybe we haven't thought of yet. So maybe you guys will come up with the next research agenda. And yeah.
So those resources were great. And I advise everybody to check them out. There is a long list of resources on that website. I was wondering also about this idea that you mentioned on embedded agency. It looked like initially that it was defined initially at MIRI, but in academia, there wasn't much awareness of this topic. And I was wondering if you see any intuitive way to interface with some of these ideas.
Yeah, I think MIRI is still like the main people working on this. But yeah, they have some like good introductory blog posts about embedded agency, which I think I'll link to that in the slides. So that's I think that's a good place to start. I'm not sure what if that's what you meant by like intuitive ways to interface with it, or do you mean like a kind of a specific example of embedded agency?
Right. So one thing that you mentioned were side effects, and to understand side effects, it seems like you also need to understand embedded agency. And I was wondering if there are some ways to introduce these concepts in classical RL environments.
Mm-hmm. I guess, yeah, that's an interesting connection. I think I think you don't necessarily need to understand embedded agency to understand side effects, because side effects can also arise in a non-embedded setting. Like you can think about like a regular reinforcement learning agent with, and you have your agent environment interface, so that's your Cartesian boundary. So it doesn't have to be like embedded in the environment that way, but it can still like cause side effects if there are some things that you forgot to specify in the reward function, like don't break the vase, then it's then you can have the side effects problem even like for a non-embedded agent. I guess, yeah, maybe the side effects problem becomes more complicated if you have an embedded agent. But yeah, I think in terms of examples, like if you have like a system that's like running in a computer, and then like it learns to like affect how much the computer is producing heat, which like causes some butterfly effects in the world or something like that. That would be like, yeah, that's like an example of an embedded agency problem. Or like, yeah, I think there are different ways you can think about it. But I think the idea is that like our present day like reinforcement learning agents are like too simple to have these issues come up. Like, for example, like AlphaGo has a particular kind of interface with the world where it's like it's just outputting Go moves, and it's like, it's not going to like try to manipulate the other player or like try to affect the political situation in the world or something, because that's not part of its action space. But then like with an AGI system, I think we would actually need to start worrying that kind of thing, worrying about that kind of thing. Yeah, I hope this clarifies things a bit. But yeah, I encourage people to like read the embedded agency post. It has some. It comes with cute pictures.
Right, that was a very great breakdown. Some people are wondering about, maybe this is kind of a personal question of whether you are worried about the how fast the AI race is going, and if you feel like there needs to be open source implementations of these models.
So yeah, I generally would say that I do worry about like the speed of the AI race. I think the AI race is like not very, not very good for safety, like safety in the general sense, like whether you're worried about like systems being misaligned or fairness or whatever other concerns, like if like different AI organizations are like trying to quickly deploy models and are kind of if they're in a race, then like I think it is a valid concern that like safety considerations, alignment considerations might get compromised in the process. So like I think one of the things that like I hope we can make happen, in the next 5 or 10 or whatever number of years, is to create more like coordination about like proceeding towards AGI at a more like sustainable pace, and having kind of those kind of collaboration on safety best practices and these kind of things that we need to like build these systems safely. Because right now, like, yeah, we can see already some of the deployments of language models are being a bit rushed and like sacrificing some of those safety considerations, like the deployment of the Bing chatbot recently, like where it had some like pretty concerning interactions with users, and that's I think that does seem like a byproduct of this like AI race environment. So yeah, I think that like I mean there was another half of the question about open sourcing, and I think we do need to be careful about open sourcing models, especially like as increasingly like with more advanced AI systems are built. I think open sourcing is not kind of an unequivocally good thing. Of course, that's that can be great for like distributing the benefits of those systems, but it can also distribute the harms of those systems as well. And I think there's like cost-benefit analysis that has to happen there, because I think if some lab actually builds AGI, I would not want them to open source it, because it could be, because in order to deploy the system safely and use it safely, then various safety best practices have to be followed, and they might not necessarily be followed by kind of all the actors who would be able to use the system if it was open sourced. So I think there are a lot of complicated questions here, and it's better to proceed quite cautiously with releasing these kind of systems. So
yeah,
I think this is the point that I wish more people had in mind, that open access and open benefits are not the same thing, and open access to powerful systems can also eventually lead to a lot of harm. So that's something that I think people should be more cognizant of.
In terms of moving with caution, is there any framework that is being used, something like a differential tech development, whereby you have guideposts, knowing that at this point, at this capability, we will have these rules about what kind of safety measures need to be taken? So I guess the same thing that could be applied for the nuclear program.
So I think these kind of principles and frameworks are currently under development. So, for example, both at DeepMind and at OpenAI, there are people working on AGI strategy and governance. So they're there are strategy and governance teams who are working on developing these sort of institutions and agreements about these things, because there are a lot of I think currently there are some missing pieces in that, where if we want to coordinate on, for example, let's say collectively slowing down AI development once a certain capability is present, then we have to be able to measure when that capability is present, and that's a whole kind of separate technical problem that needs to be solved, and there's some people working on that as well. So for example, if we have a good way to measure that this AI system has particularly advanced capabilities for persuasion or deception or situational awareness, then once it's reached a certain point, then maybe can have coordination based on that. But these are all of these kind of frameworks and agreements do have to be developed, and that's something that is not easy to govern, because it's not obvious when some kind of critical threshold in capabilities has been crossed, for example. So I guess there's a lot of work for the strategy and governance people here. I think there was maybe another part of the question that
I guess there is one more question. Maybe it's the last one. It's a question that is mainly mentioned by people, which is the digital divide. There are some countries that are they are not connected to the internet. North Korea and some parts of Africa are low resource. So the question is, AI seems to be mainly online and affecting the digital world. And most people do not see this expanding into the physical world. And the question is, do we see an AGI able to cross that bridge? This Max is saying that he's saying that he doesn't see it getting much further than the internet.
Yeah, so I think in terms of the question of how would AGI cross the bridge into having an effect on the physical world, I think one way that makes this would happen is through influencing humans. So, for example, even present day chatbots like ChatGPT and others already sometimes influence humans in various ways, or like even like some humans start to like care about these chatbots, or like maybe act differently, or have like, you know, deep conversations with them and so on. And then like I think as AI continues to advance, like I would be concerned about, like, for example, AI systems being able to manipulate people and like get them to do particular things in service of the AI's goals potentially. So I think sometimes like when people think about AGI affecting the real world, they imagine like it would control robots or, you know, act in the real world that way. But I think that's not really necessary. And it's quite possible for a language model to act in the real world by convincing humans to do things. Like, you know, we already have the example of, for example, Blake Lemoine, who thought that like Lambda is conscious and is trying to get a lawyer to represent the model and so on. Like all these kind of things where like as our AI systems, as more advanced AI systems are built, I think they will get better at just getting humans to do their bidding. And that's also like, well, I think it's important to try to measure and quantify these capabilities for like manipulation and persuasion and that kind of thing. So yeah, I would expect that AGI would be quite good at like getting humans to, you know, to manufacture things or to communicate some particular things. And like so I think an AGI system could get a lot of power just by acting through humans. So that's something that like I think we have to worry about.
I think that was all from questions. That was a very great talk. I don't know if you would like to talk a bit about your other project, Future of Life, or if there's anything you'd like to add.
Yeah, I guess, yeah, the Future of Life Institute is also like thinking along similar lines. So they've been doing various things to like increase the chances that the world does not build misaligned AGI. Like, for example, we've hosted some conferences on AGI safety in the past, and also it does some like grant making to fund AI safety research and various other things. I'm a bit less involved in FLI than I used to be a few years ago, because stay focused on DeepMind stuff now. But yeah, I think FLI is still doing a lot of great stuff. So yeah, that's it.
Thank you so much for the really, really wonderful talk and for taking so many questions.
Thank you so much for inviting me to speak and for all the great questions.